So the midterms are back. Everyone got those? Just to make crystal clear, I don't remember what the numbers are. What's the denominator? It's the total number of points. 71. So there are 71 plus 4 or 5 bonus. Okay. If you look on grade, scope, it doesn't know anything about bonuses. And so it's going to tell you it's out of 76. But what matters, and I'm sorry about the fact that these are so similar, but grade scope is going to say it's out of 76. But if you look at grade source, which is basically the grade book, it correctly will be out of 71. All right? So if you have any questions on the exam, I guess best probably just talk to me in office hours or post on the Piazza. Okay? All right, so we are talking about recurrent neural networks. Actually, so before I do that, I've got an embarrassing sort of thing, all right? So has anyone ever heard of Dancing with the Claremont Stars?
Yeah, that's watched every week.
Every week, yeah, I'm sure. So anyway, there's this Dancing with the Claremont Stars based after Dancing with the Stars. The Claremont College has one of the biggest ballroom dance student organizations. So anyway, they sent an email earlier this semester. I volunteered. So I'm going to be in that, I think it's 8 p.m. Saturday, December 8th, whatever that first Saturday after Thanksgiving is. If you want to come see, you can. Here's the deal. It neither helps nor harms you to come, right? So if you come and clap a lot, it doesn't affect anything. If you come and actually laugh and hysterically, that also won't change anything. Or if you don't show up, that won't change anything. But feel free to come if you'd like. And
where is it?
The ballroom and Pomona. Edmonds. This is called the
Snowball.
Thank you very much. So. All right. Recurrent neural networks. Let's go ahead and review. Here's what I'd like to do. I would like to fill out this diagram from last week, but I would like to do it student-led. So, Santi, would you mind starting with this? So here's the deal. You just need to add something to this diagram. Hopefully that's correct. And then we'll get someone else to come up and add some more. Would you mind starting?
What week is it?
We're going to do unfolded. Yeah, so an unfolded RNA. No. Don't talk to me.
Okay.
There you go. And actually, here's what I'm going to let you do. I'm going to let you, well, everyone else will tell you. And I'm going to let you pass that chalk on to the next person. You get to choose who that chalk goes to.
Unfolded, right?
That's unfolded, all right? Okay. And here I have a longer piece of chalk. Oh, that's cheating. Looking ahead. Yeah, look here. Take the longer piece of chalk. Could be easier to use. Right. You're not obligated to draw just one thing. You have to draw at least one thing. All right, the tiniest w sub x h. All right, but that's what it says. You don't have to do an order either. You can pick whoever you want. Zeros, all right.
Thank you.
WHH, okay? You know, actually, I'm going to do this. Let's see. Wait. You choose someone else, and you choose someone. Choose someone else. Here you go. So that way we can keep it moving. Okay, so you come on up, and then you pick someone, and they'll be right in line afterwards. See how that'll work? We'll have like a never ending.
Go that way.
And what is WHY? Okay, that's fine. She's almost done. You better hurry. Pick someone. All right. Yeah. Okay. Yeah. Well, okay. I guess. Can we finish this one? Okay. There's a B. All right. Fine. All right. And what is this whole thing? Like if I were to label this column here. Okay. Do you have a piece of chalk? No. Whoever does, where did the chalk go and where are my people? So that's something you could label. That's time step 1. Okay. Oh, I get that. All right. Not normally. Not normally, no. So there was a particular case when we talk about generation where we may need to feed that in, but not normally. I'm still not fully satisfied with time step 1, by the way. Ooh, well, I like that. Okay. Who was not standing right here waiting with chalk? What happened? Where's the second piece of chalk? You have to search, you guys? Time step 1 almost looks done, but I'm not fully satisfied. I am pretty satisfied. Oh, I'm fully satisfied. All right. Give me a loss function. Like, how would the loss function fit in here? Because I'm assuming this will be just like this one. What will it take us into the loss?
Each of the pictures you're getting each, right? But this is the part of the something that I asked about this last class, but it's like taking this, but also kind of that.
Yeah. All these, the loss can depend on all the y's.
Yeah.
So you can feed in all the y's. Some loss functions might only take some loss functions might only take the last y. Some might take all the y's. Yeah. All right. I'm not sure if there's any more, but if there is. Oh, we actually have to have something go to this. Yeah. Okay, fair enough. Does that make sense? Yeah.
Aren't there technically 2 biases? One for the output and one for the state?
There are technically 2 biases, yes. So we have a B sub h here and a B sub y here. As we have done a lot before, we commonly will just sort of ignore the biases. And then the functions for this, right, if we look at the definition for H sub I'm trying to see, because I want to make a notation change, but I hate to do that after having done this, but let's see. Let me just try something myself. WHH. Yeah, we'll just live with this. All right, so H sub t is a function of, according to this, the bias, the incoming x, and the incoming previous h, right? What sort of a function is it? Yeah, it's some activation function g, specific to h, because we will have another activation function for the y's. And we know we have a beat, right? We know we have our x sub t times wxh plus ht minus 1 whh. Yep. And then our y at any given time step is some activation on y with h times why plus or minus. So that's really all there is to an RNA. And that's what we talked about last Wednesday. And the fact you came up with this picture, I like that. That was good. Yeah.
So can I just clarify that the only weights that would ever be learned in this are WXH, WHH, and WHY?
There are 3 weight matrices, and that's all. And we're reusing the matrix from time step to time step to time step to time step. Okay? Yeah, that's a key point. So we can have this very long sequence of data with a small number of parameters. We are going to learn some ways to make this on Wednesday a little more powerful, basically by having a hierarchy of them. But yeah.
So I was going to ask, like, are they usually very large because there's only 3 matrices, or are they like?
Well, let's think about what the sizes depend on. So what does WXH depend on? Okay, so first off, we need to know how big x is. That's going to be a function of kind of our training data, right? So depending on how big x is, that's going to matter. And then the other thing it's a function of is, so WXH.
Has to be the same size as the other matrices also if you add them together?
Not quite, right? We're adding together the resulting matrices by multiplying x by w. So in particular, right, if this is x and this is w, we know that this is 1 by k. What do we know about w now? How many rows in it? Yeah, k rows, and how many columns?
X columns? Or
Nope.
any oh, W columns.
We're going to have some number, L, number of columns. How big is WHH going to be? And this is where, yes, they have to add and match. So HH is going to be how big?
So this is H1, the output of this.
So the output of, yeah. So actually, if we multiply these together, what do we get? Something of size 1 by L, right? So this guy is going to be 1 by L. And so this guy is going to be also 1 by L. And this guy is going to be 1 by L. So how big is it? If this whole thing is 1 by L, what is H sub t? What's its dimensions going to be? Actually, let me pick on someone else. Daniel.
So,
So we're looking at the dimensions of h sub t, right, any of the h's basically. We want to know the dimensions of whh, and we know the dimensions of why.
yeah.
So ht, and we know already that this is 1 by L.
Anything, or,
Well, we know this is 1 by L,
right.
and this is 1 by L, and this is 1 by L. Right? And our activation function retains our dimensions.
Yeah, well, I thought the product XT or WXH is 1 by L, and then the product of HT minus 1 WHH is 1 by
Yep.
L.
Yep.
But then I thought the question was how big HT minus 1 there would be. And
Yeah, ht or ht minus 1, because they're all going to be the same. They're not going to change.
yeah, don't we set that?
Well,
And
yes,
that's-
we do. I guess what I'm saying is since this is 1 by L, and this is 1 by L, and this is 1 by L, their sum is 1 by L.
Yeah.
Our activation function maintains the dimensions, so it ends up at 1 by L. So h sub t, the form of h, at any given time step, is 1 by L. Yeah. Does that make sense? So this is basically just the size of our hidden state. It's one of our hyperparameters we get to choose. How much state information do we want? If we only keep one piece of state information, right, a vector 1 big, it's not keeping a lot that it's maintaining over here, right? It's got to stuff a lot into that one floating point number. If we have it 1,000 big, it's got a lot of room. It can sort of maintain information from time step to time step to time step to time step. Does that make sense? So how big is WHH?
L by L?
Oh, by L, yep. And HY? Well,
HY would be L by whatever your
L by whatever.
transferred y.
Yeah, whatever our output is going to be. Does that make sense? All right. So we get to decide how much hidden state we want to keep. The amount of hidden state we keep changes the size of our matrices. Okay? So if we have twice as much hidden state, we have our matrices are twice as big.
So WHH is supposed to be L by L, but is it supposed to be L by L also over there? Maybe you should
Here?
Yeah. Sure.
So this product is 1 by L. And let me make sure that I mean that here too. The product is 1 by L. Right, because we got a 1 by L times an L by L. Which will
And
give
so that first weight matrix, like that's
this one.
SH.
This is XH, yep.
Okay. Very good.
Yep, exactly. All right, I see some puzzled looks, and so just kind of throw out some questions.
So are these weight matrices contain the parameters we're trying to train?
The weight matrices, along with the biases, are the parameters we're trying to train. Yes. So we're going to next step into backpropagation and look at exactly how they're getting updated.
I have two questions.
Yep.
How did we know the first dimension of WHH? How do we know it's L?
I made up L right here. I said, let's call this L. And once we've called this L here, that forces everything else to be L.
Oh no. Oh.
Since this width is L, right? Yeah.
Okay, that answers both.
Yeah. So basically, that's our one choice we get to make. How big is our hidden state? And then that forces completely forces this matrix and forces one dimension of each of these matrices. Other questions?
The one in HT, where did that come from? That was a choice.
The 1? No.
1 by L.
The reason for the 1 is x sub 1 is a 1. But actually, we're assuming here we have a mini batch of size 1.
Okay.
This is kind of how we normally have looked at things, was that X was, some 1 by something. And input.
And
If we had a mini batch, it would actually be of size K, it would actually be K times N. Just as in convolutional neural nets, we can feed in this mini batch of inputs. We could do the same thing into an RNN. But it's easier not to think about that. It's easier just to think about it as 1 by. But this 1 by is what forces this to be a 1 by.
and they're always going to be one-dimensional, two-dimensional matrices in all cases.
Could we have a multi-dimensional?
Is everything fully connected at this point?
Well, we're fully connected because that's what this weight matrix does, is this causes fully connected and
So
fully
I guess it
connected.
wouldn't matter if it was flat.
Wouldn't really matter whether it was flat or not. Yeah. There's another question somewhere. Was that not? Yes.
Okay.
Yeah.
I guess I'm kind of
Here, I'll give you a token. You can talk. Go ahead.
Okay. I guess I'm kind of confused why it seems like the size of HT is changing. Like in the first one here, we got HT minus 1, right? Like
Here.
Yeah. So the size of that isn't going to be 1.
Oh, it is going to be 1 by L.
It is.
And here's the reason. WHH is of what size?
Mobile.
1 L by L. So therefore, it forces us to have the second dimension of it be L,
Right.
and the first dimension is going to be 1.
Okay.
So HT is 1 by L, HT minus 1 is 1 by L.
Okay. Got it.
Yeah, all the way through. So our hidden state contains the information that we have captured so far. It contains everything that is of interest from the previous X's. Let's look at backpropagation, which we looked at a little bit, but let's look at it in more detail. So there's a fancy name for it. BPTT, backpropagation. Through time. But in fact, it's just backpropagation, viewing it as going through the unrolled RNN. So the only real difficulty, let's look at an example. I'm gonna use a slightly abbreviated diagram here. So I'm gonna just show x1, h1, y hat 1. I'm going to call this h0 coming in. Usually it's zeros, but it need not be. In fact, we'll describe today cases it's not. Let's see. And then I'll just label this with our weight matrix. So this is WXH, WHY, WHH. Does that make sense? Now we're doing this where, and this is a WHH. So we don't have the explicit plus in here, the fact that we're adding these two together and applying an activation function. So that goes on. So eventually, let's do our last guy. So let's say our x is a vector of size n. Right, so that will end with h sub n. Unlike a CNN, right? Remember in a CNN, the number of layers is fixed when we build the network. Here, the number of layers depends on how many inputs we put in. Right? If we put in 5 inputs, then it's 5 time steps deep. And if we put in n inputs, it's n time steps deep. So in this case, we're putting in n inputs And so it is n times steps dpn.
Are time steps the same thing as a layer?
So it acts a lot like a layer, but RNNs are actually just one layer themselves, which kind of, you could think of it as sort of expand at runtime to be this little for loop that opens up depending on how many x's there are. So we've got our loss function. And what we know, let's just say all the y's go into the loss function. Right? If we're trying to do sentiment analysis of a sentence, we don't care about this y or this y or this y. We just want to know at the very end, was it a positive or negative review? Okay? But there are other cases where we definitely care about these y hats. Like if you're trying to caption an image, you want to know the words in the caption, for example.
Since that can vary in different cases, for RNNs, is there a standard loss function where if say you only want y sub n, you just basically set all the other ones to 0, or
Nope.
is it different loss functions every time?
Different loss functions. So you can specify when you get the output of one of these, commonly, Keras does this, do I want for this RNN just the last y, or do I want all the y's? And so the shape of your output is going to be different. You'll have an extra dimension if you ask for all the y's. And this guy just outputs as well. It still has an h, this h sub n that would be output. So we are interested in computing the gradient with respect to all of our weight matrices, right? Because that's what we're going to be updating, our weight matrices and our biases as well. And conceptually, and this is just the same way backpropagation we did before, conceptually, we're just finding each path to a weight matrix, from the loss to the weight matrix, finding the path, finding the derivatives across all those paths, multiplying them together, across a path, find the derivatives, multiply them together, and then sum that for all the paths. So for each path, find what that path contributes to the gradient, sum that for all paths. We don't implement it that way because it would be exponential, but conceptually that's what we're doing. And then practically what we do is we just move back layer to layer to layer, compute all the gradients here, and then compute all the next gradients and the next gradients. And that's what we're going to be doing as well. So if we want to compute the loss of, and here's what I'm going to do. I'm going to ignore the fact that these are all the same WHYs. Okay? I'm going to actually call this one WHY sub 1 and WHY sub 2 all the way to WHY sub n. And I'm going to do the same thing for the XHs and the same thing for the WHH. I guess we'll call that one n minus 1. Does that make sense for now? Okay. So if we want to compute WXH sub n, how many paths do we have from a loss function to here?
I'm not sure.
So if we look at the arrows, how many back arrows can we traverse to get to this back arrow?
1.
1. To y hat sub n, and then down to h sub n, and then to here. So the way we would actually do that is we'd look at the loss with respect to y hat sub n, times the derivative of y hat sub n with respect to h sub n times the derivative of h sub n with respect to w x h sub n. Standard stuff. So there's some activation functions in part of these, and so we got to take the derivatives, of those and so on. But we can do that. Yeah.
What happened to WHY sub n?
That's subsumed kind of in here. So how do you get from h sub n to y hat sub n? You multiply by WHY. I see. So yeah, we skipped this one as far as calculating this. We do need to calculate this. So let's look at that one too. Sure. So we want to know WHY sub n. Yes? Does that make sense? And for completeness, let's go ahead and put in the last weight matrix, which is HH. And I'm going to abbreviate it a little bit. So I'm going to just say, let's figure out the derivative with respect to h sub n, and then go from h sub n to WHH minus 1. Right? Because we're going to already have to calculate the derivative of the loss with respect to h sub n to calculate this matrix. And so that's what we take advantage of to calculate this matrix as well, to calculate the gradient of that matrix. Okay, so that one is fairly straightforward. It's when we get to the next one that it's a little more complicated. Instead of going from n minus 1 to n, I'm going to just go from a generic time step. Let's say from time step t. Calculate at time step t. So we know we're somewhere in here, h sub t, okay? And we want to know these matrices. The W, X, H sub t, this matrix and this matrix. So let's look at first, let's just calculate h sub t, because we're going to want to use that for a couple of our matrices. Now let's use this. Let's do the simple one first. So the simplest, what would be the simplest one? The one with the fewest paths. This arrow, or this arrow. Matt. So we've got the three arrows are this guy, which is W, H, Y sub t. This guy, W, X, H, T, or this guy, W, H, H, T minus 1. Which has the fewest paths from the loss to it? HY. Yeah, we only got one path. The only way to get to here is through Y hat sub t. Yes? So that's an easy one. Just like the others. Sorry, just like the ones we just calculated down there at the very end. So this is W, H, Y sub t. And it's going to be the loss to Y hat sub t times the derivative from Y hat sub t to W, H, Y t. Okay? Now it gets more complicated. If we had the gradient to h sub t, it'd be easy to find these two gradients, right? Because there's only one path from here to here. So the interesting one is that derivative. How many arrows are pointing out at h sub t? Susan?
2.
2. So if we've got 2 going out, then in order to do our derivative, we've got to sum the 2 coming in. So 1 is coming from up top. So let's look at that one. So that's going to be the loss to y hat times the derivative from y hat to h sub t. Okay, so that takes care of this loss here. Right? But we know we have another path. The other path is from h sub n over to, kind of from the right. Now from the right, there are lots of other paths to get up to here. But as long as we know the derivative from the loss to h sub t plus 1, we know how to get back to h sub t. So we're going to sum now the loss to h sub t plus 1, and then multiply that by the derivative from t to t minus 1. Good day.
I think last class we talked about cases where like the input at the next time step is sampled from the output of the RNN at the current time step. Would that change like the backpropagation for the WHY? Because then it like can flow through the output to the next input and then back out?
Yes, well, so normally when we're doing this let's see, let me think about this. It seems like it, but I'm going to have to think about that. So normally when we do generation, we actually have already trained it. And when we're doing that generation and feeding in the next one, we're let's see. We're not directly, let me correct that. So we're not directly feeding in this output into the next input. We're going to do a sample and feed it in. And that will be with an already trained network. So I don't think we have to worry about that. Okay. So we're going to take the loss. We know how to compute h sub n. We know how to compute all the intermediary h's all the way back to h sub 1. And once we have the h's, we can compute the weight matrix for x and the weight matrix for the previous h. Yes?
I'm confused with this function. Is the last one supposed to be h sub t or t minus 1?
T. Yeah, that fits better.
Then the numerator, I think, needs to be t plus 1 on the second term.
Let me just look at the second. Does this match this? Yeah, so they cancel out. Yes, to t, only to t, t. Yes, that is correct. Thank you. Your hand now goes down because that answers that. Okay, thank you. So what I said is that we are going to do these computations as if every one of these weight matrices was distinct. But they're not. They're tied together. They're shared weights. Right? Because this matrix is the same as this matrix, is the same as this matrix. But the gradients may be different. Can you see how that is? Can you see how the gradients for this at time step 1 can be different from time step 2, can be different from time step t, can be different from time step n? How do we handle these competing gradient manipulations that we want to have happen to this weight matrix? We just basically let the weight matrix get pulled in all directions. Just sum it all up. So if this guy wants to go over in this direction, and this guy wants to go over in this direction, well, who wants to go farther? You know, this guy's pulling more, so we'll go over this way a little bit. But not too much, because this guy doesn't want to go, right? And there's the up direction and the down direction and all the other directions. Basically, the values for each of the entries in the weight matrix. So basically what we say is WHH is going to be just the sum from I equals 1 to n of the gradient is going to be the sum of the gradients. Okay. So we take the HH's from for the H's, we're doing from 0 to n-1. For all the others, we're going to go from 1 to n. Okay, and similarly for the y. Sorry, yes, similarly for the y. So it's not particularly different than how we've actually done updates in the past. We said you look at the gradients across all the paths and sum them up. Well, we took the path to get to here, and we took the path to get to here, and we took the path to get to here. Since it's the same one, we just sum them all up. Same way. Yes.
Say our output was like something that was like binary, like a mood, like happy or sad or something. Would there ever be a reason to compute the loss at every step? If you have an output and then almost like adjust as you go along. So like time step 1, time step 2, back.
Yeah, you could.
And then like so you're kind of learning as you're.
Yeah, you're kind of saying, well, I know how this story ends, right? It ends positive, and let's just after 3 words, let's just see. Are you looking positive? Because it wouldn't hurt to be pushing you to be positive. So yeah, we could certainly do that. We could say, even though we actually only care at the end about this one, let's try and push these all to say that it's positive. And that would have a couple of advantages. One advantage is, if this is very long, right, if this is a very long sequence, again, we have this problem of getting the, if we only go through y hat sub n, then we've got to go through here to get all the way back, right? And this is a long way, and we run into the problem of vanishing gradient. Instead, if we said we want to feed in at intermediate points in time, it's sort of like the inception network, where we had the loss, we had our output at the top, but then we had kind of some intermediate outputs along the way to try and force some gradient loss down. So yeah, that could work.
If they're the same matrix, how do we have the gradient loss?
If they're the same matrix, how do we have the gradient loss? Well, let's say we have a very simple hidden state with one value in it, okay? So that these matrices are very small. And let's say we're doing like sentiment analysis, okay? So we have a word coming in here, I don't know, that doesn't really have any effect on the sentiment analysis. And so the gradient for this would be 0, right? This just is neither helping nor hurting. Given that the word is it doesn't matter whether we adjust the weights for this, right? But this word is incredible. And this word is sucks, okay? So the loss function for the word sucks is going to be forcing a fairly different way from the word incredible. So one of them is going to try to be forcing this hidden state to be saying kind of this is negative-ish, and one is going to be forcing it to say positive-ish. But it's the same matrix, and so they'll both be kind of doing some fighting. Yes.
And this get used in like real-time monitoring, like if we're trying to like track a signal.
So this is used in your, you probably don't have them in your, well, here, yeah. So if I say, well, my phone is over there. If I say, okay, Google, right, or hey, Alexa, that is using an RNN. and it's taking samples at small time steps and just feeding those time steps through and just kind of waiting until it's got a y hat that says, hey, oh, they just said it. Hooray. Okay? So it's exactly a case, I think, that you're discussing where you have this real-time sample, yeah.
So a little tangential, but so Alexa is continuously listening. Like, is that the only way that they would know? Or like Alexa would know whether or not we're saying Alexa is if they're continuously. Like,
No, you
yeah,
could
it sounds-
you could say, have a button on it, and say, only when you hold the button down, then you have to say, Alexa.
That kind of defeats the purpose.
It kind of does defeat the purpose, yes. It's listening all the time. What it's not doing, and you can check this with the network traffic analysis, is it's not sending it back to the cloud. It's locally checking. Once it hears Alexa, then, oh my God, let's grab this stuff and send it up to the cloud. Yeah, so avoid saying Alexa at times you wouldn't want that all stuff to all be going to the cloud. There's another question? Okay.
How do we avoid, it seems like because the channel through the loss goes through the same rate so many times, it seems like the grades explode very quickly and vanish very quickly.
Yes, indeed.
Okay. So it's like a very narrow range of what these weights can be before we have something.
Yeah, so there are a couple ways to deal with that. The biggest way is these long short-term memory that we'll talk about in 2 weeks. But I'm going to describe something right now that we deal with long sequences. So it's called truncated BPTT. So it's parameterized. I'll just say K1 and K2, where K1 and K2 are between 1 and n, with K2 no smaller than K1. So n is the sequence length. So basically what this means is you take K1 steps forward, just normal forward propagation, and then K2 steps of backprop, BPTT, backprop 2 time. So what we have just been talking about, what are the values of K1 and K2 that we're looking at, Willow? Like the way we just described here, if we have an input of length n, how many forward steps do we do? N. And how many back steps then do we do? Well, according to this picture, we're back propagating all the way to the beginning. So n, yeah. So this is the traditional BPTT. Okay? So we can basically just look at it if let's see, if this is 1, 2 to n, so this is our input, we basically go forward, and then we go backward. What might be some disadvantages of this? Nick?
The traditional,
Mm-hmm.
it's a long ways back to the first.
Okay, there's a long ways back, and there are a couple problems with that, or potential problems, but it is a long way back. And a long way back, we run into 2 problems. Rachel, can you see a problem?
Is this addressing vanishing gradient?
Yeah, we definitely have the vanishing gradient problem. What else? Keep in mind, in order to do backward propagation, we need to store the results of the forward propagation, right? In this case, there's not a lot to store, but what do we need to store? We need to store basically all the activations, not at each layer, but at each time step. So if n is 10,000, we've got to store all 10,000 of those activations, all those H's, all the way in order to be able to do the back propagation. So it could take a lot of space. Lots of memory. And vanishing gradient problem. Really, we have exploding gradient problem too, but we have things we can do about that. Okay, right? Because we can clip. So we can try some different values of K1 and K2. We could try, for instance, N1. Sorry, we can't do N1. Why can't we do N1? Because K1 has to be less than or equal to K2. So we could do 1N. So what would that look like? We would take one step forward and then N steps back, but we run out. So we'd go like this. And then it'd be 2 steps forward, 2 steps back. Sorry. 1 step forward again, 2 steps back. 1 step forward, 3 steps back. 1 step forward, 4 steps back. Is it going to be faster or slower than the, so is 1N going to be faster or slower than NN? Slower, because we do the same amount of forward propagation in aggregate, but we do order n squared back propagations, right? Because at the end we're doing n back propagations, n minus 1, n minus 2, and so on, right? At the very end, it's like that. So this is NN. This is 1N. There are other choices. We can do, I can write it on top, I guess. A crude approach would be to do KK. So go forward K, go backward K. And then go forward K, go backward K. Till we get to the end. Maybe we have a small one at the end. Right, add up to 10. One N has the advantage over N and N that the early time steps are going to get the gradient updated nicely, right? Because we've got all these initial ones where it's not very long, where we have a chance to push back to that weight matrix based on the first input. Right? This is slightly different from having a deep layer network. Right? In a deep network, the problem is these weights at the beginning never get updated. Here, our weight matrix is getting updated all the time. The problem is, in this case, it isn't getting updated to take into account the first input very well, because we may have potentially lost our gradient. May have. Depends on our loss function. If our loss function includes all the y-hats, that first time step will update just fine. But if it only includes the last time step, then this is going to have a really poor showing. And I guess if it includes only the last time step, you wouldn't want to use a 1N. Because what does it mean to go forward one time step and then back if the output is way down the road? So KK looks like this. Basically, it just says take your input and just break it into chunks of K. It's almost that, but it's not quite that. So if we had something of size n, this is our input, and we break it here, and we say, okay, we're going to feed this of size k into our network, and then we're going to feed this of size k into our network separately. So first just feed this. We do our forward propagation, we do our backward propagation. That all works fine. If we now go to feed this in, we have a problem. Because if we feed this in to this network, what's this weight matrix? The incoming, I'm sorry, not what's his weight matrix. What's h sub 0? What do we say we normally set it to? Zeros. But really, if you look at it, right, so we're going to say this ends up at h sub k, and then this is h sub k plus 1, right? What should be feeding into here? Should it be all zeros? It should be h sub k. So there's a facility for doing that in Keras and in PyTorch and so on, where you can say, no, don't use zeros. I have a good matrix for you to use. It happens. I said matrix. I do not mean matrix. Don't use a zero state. Use a state I am giving you from a previous calculation. So we would actually feed in here the old h sub k. And so then conceptually this now is going to be, this is not really x sub 1, right? It's really x sub k plus 1 getting fed in h sub k, and so it does all the correct calculations from then on. Does it make sense? A problem is we have a seam here, and we're not propagating any errors across the seam. Right? So there's no error across the seam. We can fix that. We could do, for instance, a, I don't know, K2K. K2K would look like the same beginning. And then we go here, and then we backprop here, right? And then we go here, and we backprop here. So we are filling in the error across the seam. But if you're using Keras, you have to program this one yourself. Because basically what they give you is NN with the ability to feed in initial h sub zeros, which means you can implement a KK. Okay? Okay. Let's try that one. Okay. Questions? So what we have looked at is how to do our backpropagation. This backpropagation through time, which is really just backpropagation with the same chain rule that we have used before. We conceptually think of our weight matrices at the different time steps as different, and then just add in the gradients, sum together the gradients for each of them. And then we talked about this truncated BPTT to deal with these really long sequences, so we don't have to backpropagate through the whole thing.
Is there like a value, like how do you choose K? Like is there like a trade-off between like higher and smaller Ks? Or
If you're doing a KK, right, it's how much context do you want here? And also what's going to fit in your GPU is going to be a lot of it as well. So
do you usually make it like as big as will fit on your GPU? Is that trade-off?
it's a trade-off between that and a batch size, right? Because you're fighting against the multiple of batch size times k is what's going to limit your memory. All right, I want to give you an example. We will talk at length next week about language models. Language models are used to predict a word, like the next word in a sequence, or a missing word in a sentence. So you can imagine kind of how this works. You feed in a word, and another word, and another word, and you keep going. And then at the end you say, okay, what do you think is the next word? Right? So if you had, for instance, I don't know, Joe threw a ball to the I don't know, let's say that's the word that we're predicting. Okay, so we feed in first Joe, and then through, and then a, and then ball, and then to, and then the, and it's going to predict this word. How's it going to predict the word? A big softmax over all the words in our dictionary. What might be higher probabilities and what might be lower probabilities for what fills in here? Right.
Now it's going to be higher, relatively. Are you looking for specific words?
Okay, so like for instance, oyster's pretty high. Is that what you're saying?
Certain now.
Okay, like
Fence.
fence? Okay.
To the wall, I don't know.
Oh yeah, okay, I get it. Wasn't what I was thinking, but I get it.
Dog.
Dog, yeah, dog can work. Yeah, those would be higher than oyster and higher than the. No, the actually is not that low. To the quickly, yeah, that'd be a low one, for example. Adverbs be pretty low. So, okay. Does that make sense? All right, so let's do this one. Joe gave the orange so what might be now? In fact, we decided this is a noun next, right? Probably. What's this?
Away.
Away?
Joe gave the orange away.
Okay, away could work.
Fence.
All right. Actually, I'm going to change my problem slightly. I'm going to change my problem slightly and actually make it better to what you had here. So let's say we're going to simplify the problem. We are going to actually be labeling these. So article, noun, what's this? Preposition, article. Okay, so our choice here, we decided adverb is bad, right? So not adverb. So this word, what is it? I'm sorry. We're just doing this labeling problem. We'll talk about the language models in a moment. Noun, proper noun, I guess. Verb, article. What's this one?
Could be both.
Both.
Noun and adjective.
Okay, yeah, nouns and adjectives. So it could be noun, could be an adjective. We don't know. What information would you like to have in order to determine that? The next word. Yes. That is what is going to lead us into a bidirectional RNN. So a bidirectional RNN says, great, we can feed the stuff in from the beginning. It would also be nice if we had the information from the other direction. Now, this will not work in a real-time situation, right? You don't get to, listen for the word Alexa in the past. Said, you said Alexa 5 minutes ago, didn't you? Yeah, not useful, right? But if you've got your entire input, then you could go through it front to back. You could go through it back to front. And so basically what we say is kind of the equivalent of just feed it in from back to front. So if it's gave the orange to the fence, then we know it's a noun. But we know it's a noun because we see the context on both sides. Okay. Maybe it's enough to just read it from here. Fence, the, to, orange. Can't be an adjective, right? Would have to be a noun. So in this case, we can probably determine it just from going from the right. But sometimes you actually need both sides in order to determine this. And when we say both sides, not necessarily just the word on each side. Okay. Sometimes the context depends on something way before. So, he gave something, 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 something. Do you want to use his or her here? Well, it depends on what the gender was of the first word. Or sometimes you may need to wait till the end of the word to know what's the end of the sentence to know what's going on. Apparently, German is well known for that. It's going to set stuff up and go and go and go, and at the very end they throw you like a verb or something and says, "Oh, now I understand what you meant, 15 words ago," by giving you them. So, bidirectional RNN is conceptually very simple. Basically, it's like we're going to have one RNN, we're going to feed things through front to back. And we're going to have a totally separate RNN, trained separately, that we feed things in back to front. So we're going to have x1, h1, y hat 1, h0, h2, x2, y hat 2, to hn, xn, y hat n. Right, and if we want to label these, wxh, why, and whh. I am going to add a little symbol. I'm going to use a right arrow for the h. So these are the forward h's. And these are the forward weight matrices. Okay? And then I'm going to construct another network with backward weight matrices and backward h's. So this matrix, this RNN is going to calculate h sub n first from an incoming h sub n plus 1, which is normally going to be zeros. But if I have this truncated BPTT, I might be doing these chunks of k, and so maybe this is actually from the next part of the sequence. So this is going to be a left arrow h. And it is also going to feed into y hat sub n using a left arrow hy. And it's going to also get fed in the same x sub n. Right? This kind of just wraps around here. Same x sub n, except using a left weight matrix. And then we're going to go to the left with WHH, left arrow. And here we have an h sub 2, and here we have an h sub 1. No, that's an h sub 0. So it's really just two completely different RNNs that feed in to the same y hat. So the y hat at y, that's hat, at time t is g sub y. And just like we had before, we will take h sub t, whh, but that's going to be the right versions. I'm going to also add in the left versions. And I'm ignoring biases here. But we could add both biases from each direction. So, hold on just a second. If we get to here and we get to orange, the forward BPTT, the forward RNN is going to say it's either a noun or an adjective. But I know it's not anything else, but I know it's either a noun or an adjective. And the backward PPT is going to go through and say fence the to orange can't be an adjective because I don't have a noun here next to it, right? It wouldn't make sense that this is an adjective. So it's going to say this is a noun. And so the combination of them is going to say, on the one hand, it's either an adjective or a noun. On the other hand, it's a noun. It's a noun. So they'll be merging that information. You had a question?
I was like, do you, for these words, like, do you give like a list of like, oh, these are words that are nouns, or like, does the model actually like, need to learn what are nouns and verbs?
It would need to learn what are nouns and verbs through supervised learning, right? You would basically have a bunch of labeled sentences where you have what all these parts are, and you'd feed it in. And you'd basically say, you'd feed in Joe, and it's going to feed it out a Y hat that says, I don't know, it's one of these 10 different things, and random probability what it is. And then you do gradient descent, right, backwards prop, and you say, no, bad, make it more of a noun. And then you'd feed in this one, and you'd go through that. Like, so it'd be crappy. Over time, it'd get better.